and line-to-line fault, such as one caused by damage to an alternating current circuit cable, creates a low impedance path between two live conductors. This causes a high current surge that trips the main breaker. The alternating current breaker is designed to protect against overcurrents in the branch circuit it is serving. In this case, the fault current flowed outside of the branch circuit, so the alternating current breaker did not detect it. Regarding circuits tripping in a sub-panel, it is possible that the oil breaker in the main panel was faulty. Breakers can degrade over time and may not trip at their rated amperage anymore. Breakers of the same model and size can trip at slightly different amperages due to manufacturing tolerances. However, this difference should be minimal and typically not significant enough to cause a circuit to trip that did not trip before. There are other possible causes to consider. Firstly, check that the circuit was wired correctly when it was moved to the sub-panel. Secondly, ensure all connections in the sub-panel and at the load, such as an outlet or appliance, are tight. Thirdly, check if the circuit is overloaded by adding new loads or redistributing loads to other circuits. Finally, test the device connected to the circuit to rule out any internal faults. To elaborate on why a line-to-line fault might trip the main breaker instead of the branch circuit breaker, let's consider how breakers work and the nature of fault currents. Breakers are designed to trip when they detect an overcurrent situation. This overcurrent can be due to a short circuit, an overload, or a ground fault. A short circuit, like a line-to-line fault, is characterized by a very high current flow because the electricity is taking an unintended path with very little resistance. An overload occurs when too many devices are drawing current on a single circuit, exceeding the breaker's rated amperage. A ground fault happens when current leaks from a live wire to a grounded surface. In the case of a line-to-line fault, the current flow is extremely high and rapid. The magnitude of this current can be so great that it exceeds the interrupting rating of the branch circuit breaker. The interrupting rating is the maximum fault current that a breaker can safely interrupt without failing. If the fault current exceeds this rating, the breaker may not be able to trip quickly enough or may even be damaged. The main breaker, on the other hand, is typically rated for a higher interrupting capacity than the branch circuit breakers. This is because the main breaker is designed to protect the entire electrical panel and all of its branch circuits. In a line-to-line fault scenario, the fault current may flow through the main breaker before it reaches the branch circuit breaker. If the main breaker detects the overcurrent first and its interrupting capacity is sufficient, it will trip, cutting off power to the entire panel. The branch circuit breaker may not trip at all because the main breaker has already interrupted the fault current. Another factor to consider is the impedance of the wiring. Impedance is the total opposition to current flow in an alternating current circuit, including resistance and reactance. The impedance of the wiring between the fault location and the main breaker may be lower than the impedance between the fault location and the branch circuit breaker. This means that the fault current will preferentially flow through the path with the lower impedance, which may be through the main breaker. Regarding the issue of a circuit tripping after being moved to a sub-panel, there are several possible explanations beyond a faulty breaker. Firstly, incorrect wiring is a common cause. When moving a circuit, it is crucial to ensure that all connections are made correctly. This includes the hot wire, the neutral wire, and the ground wire. If any of these wires are connected incorrectly, it can cause a short circuit or a ground fault, leading to the breaker tripping. Secondly, loose connections can also cause problems. Over time, connections can loosen due to vibration or thermal expansion and contraction. A loose connection can create a higher resistance point in the circuit, which can generate heat and eventually lead to a breaker tripping. It is important to check all connections in the sub-panel and at the load to ensure they are tight. Thirdly, an overloaded circuit is another possibility. Even if the circuit was not overloaded in the main panel, it may become overloaded in the sub-panel if new loads have been added or if loads have been redistributed in a way that exceeds the circuit's capacity. It is important to check the total current draw of all devices on the circuit to ensure that it does not exceed the breaker's rated amperage. Fourthly, a defective device connected to the circuit can also cause the breaker to trip. A device with an internal fault can draw excessive current, leading to an overload or a short circuit. To rule out this possibility, it is important to test all devices connected to the circuit to ensure that they are functioning properly. Finally, it is worth considering the possibility of nuisance tripping. Nuisance tripping occurs when a breaker trips for no apparent reason. This can be caused by a variety of factors, including voltage fluctuations, electromagnetic interference, or even a faulty breaker. If you have ruled out all other possible causes and the breaker continues to trip, it may be necessary to replace the breaker. Here are some additional details regarding electrical breakers. Electrical breakers, also known as circuit breakers, are essential safety devices in electrical systems. Their primary function is to protect circuits from overcurrents, which can result from short circuits, overloads, or ground faults. When an overcurrent occurs, the breaker trips, interrupting the flow of electricity and preventing damage to equipment and wiring, as well as reducing the risk of electrical fires. There are different types of breakers, each designed for specific applications and current ratings. Standard thermal-magnetic breakers are the most common type and are used in residential and commercial applications. These breakers use a thermal element to detect overloads and a magnetic element to detect short circuits. When an overload occurs, the thermal element heats up and bends a bimetallic strip, which trips the breaker. When a short circuit occurs, the magnetic element creates a strong magnetic field that trips the breaker. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults. These breakers detect imbalances in the current flowing through the hot and neutral wires. If a ground fault occurs, the GFCI trips, interrupting the flow of electricity and preventing electric shock. Arc fault circuit interrupters, RFCIs, are designed to protect against arc faults, which are dangerous electrical arcs that can occur due to damaged wiring or loose connections. These breakers detect the unique electrical signatures of arc faults and trip, preventing electrical fires. Breakers are rated by their amperage and voltage. The amperage rating indicates the maximum current that the breaker can carry without tripping. The voltage rating indicates the maximum voltage that the breaker can safely interrupt. It is important to use breakers with the correct amperage and voltage ratings for the circuit they are protecting. Breakers also have an interrupting rating, which indicates the maximum fault current that the breaker can safely interrupt. It is important to use breakers with an interrupting rating that is sufficient for the potential fault currents in the circuit. When selecting breakers, it is important to consider the specific application and the potential hazards. For example, in residential applications, it is important to use GFCIs in bathrooms, kitchens, and other areas where there is a risk of water exposure. It is also important to use GFCIs in bedrooms and other areas where there is a risk of arc faults. Regular inspection and testing of breakers are essential to ensure that they are functioning properly. Breakers should be inspected for signs of damage or corrosion. They should also be tested periodically to ensure that they trip at their rated amperage. If a breaker fails to trip when it should be replaced immediately. In addition to breakers, fuses are another type of overcurrent protection device. Fuses are similar to breakers in that they interrupt the flow of electricity when an overcurrent occurs. However, fuses are one-time devices that must be replaced after they have blown. Breakers, on the other hand, can be reset after they have tripped. Both breakers and fuses play an important role in protecting electrical systems from overcurrents. In summary, understanding how breakers work, their different types, ratings, and applications is crucial for ensuring electrical safety. Regular inspection and testing, along with proper selection and installation, are essential for maintaining a safe and reliable electrical system.